In section 8.3, we're going to study similar polygons. In order to study similar polygons, let's first look at some shapes. Here is the original picture, and we have three choices, A, B, and C. If we look at A looks like the picture is too tall. A looks like my picture has been squished this way or stretched vertically. B looks like the picture is too short and fat. It's like this original picture has been squished down. C, on the other hand, looks just like the original. So if I had to pick a shape that was similar to the original, I would pick C, because C, the picture has been kept in proportion. If we look at A and B, both of these look like the picture has been distorted. A looks like we've squished horizontally. B looks like we've squished vertically. So let's look at some numbers and try to pick out similar shapes. If we have the dimensions of a rectangle and the dimensions are 5 by 7, which of the following dimensions are similar to the original? If we look at A, to go from 5 to 3 and from 7 to 5, we've subtracted 2 from both the height and the width. If we look at B, we've subtracted 2 from just the height. And if we look at C, to go from 5 to 2.5 and to go from 7 to 3.5, we've divided by 2. The same as dividing by 2 would be to multiply by 1/2. So which of these keeps similarity? Which of these methods keeps proportionality? Well, even though we've subtracted 2 from the same amount, or subtracted 2 from both the height and the width in A, subtracting actually doesn't keep proportionality. The only way to keep proportionality is to divide or to multiply. So C is the one that is similar to the original. If we apply these dimensions to the pictures, you can see that, yes, C is the one that keeps proportionality, because I've divided both the height and the width by 2. If we look at this first one, A, when I subtract 2 from the width and I subtract 2 from the height, subtracting 2 from 5 is almost half, and subtracting 2 from 7 is about 1/3. So when I subtract more from the width than I do from the height, I end up with a distorted picture. If I subtract just from the height, I end up with a squished picture. My width is the same, but my height has changed. So how do we mathematically define similar polygons? Well, two polygons are similar if, number one, their corresponding angles are congruent, and number two, the lengths of the corresponding sides are proportional. So there's two things that have to be true in order for shapes to be similar. Corresponding angles are congruent, and the corresponding sides are proportional. The symbol for similar is kind of like our congruent symbol without the equal sign. It's just this squiggly line, and this squiggly line means similar to. Let's think about some of the quadrilaterals that we've studied. If we look at squares and rectangles, are squares and rectangles similar? Well, squares have 90-degree angles and rectangles have 90-degree angles, So my angles are going to be congruent between squares and rectangles. But the lengths of the corresponding sides are not always going to be proportional. So squares and rectangles are sometimes similar. If I look at squares and rhombuses, squares and rhombuses are going to meet number 2. The sides are going to be proportional, but our angles are not always going to be congruent. So squares and rhombuses are just sometimes similar. If we look at all squares, well, squares always have 90-degree angles, so our corresponding angles are always going to be congruent. And our corresponding sides are going to be proportional. So all squares are always similar. Let's look at some examples where we have to decide if the following are similar. These first two are going to be parallelograms. And these two parallelograms are going to have corresponding angles congruent. So we've met the first criteria. Between these two, we do have congruent angles. So let's check to see if the sides are proportional. To check to see if the sides are proportional, I'm going to set up a proportion. I'm going to have a ratio equaling a ratio. Now I can set up this ratio a couple different ways as long as it's consistent. I'm going to start with this side right here, 4. And I'm going to compare 4 to 3. And then I'm going to hop to this side, 6, and I'm going to compare 6 to 4.5. I'm consistent because I go from this parallelogram to this parallelogram, and from this parallelogram to this parallelogram. To check to see if this proportion is true, cross multiply. 4 times 4.5 is 18. 3 times 6 is 18. So are the following two polygons similar? Yes. Our corresponding angles are congruent, and our sides are proportional. Let's look at these two rectangles. A rectangle will always have 90-degree angles. So we've met qualification number 1. Our corresponding angles are congruent. Now let's check to see if our sides are proportional. To see if they're proportional, again, set up a proportion, a fraction equaling a fraction. So I'm going to compare 4 to 7. And then I'm going to compare 6 to 9. To check to see if they are proportional, cross multiply. 4 times 9 is 36. 7 times 6 is 42. So even though these two rectangles meet qualification number 1, all the angles are congruent, the sides are not proportional. So no, they are not similar. Let's look at another problem. The two isosceles trapezoids are similar. Well, we already know that they're similar, so we know a lot of information about these two isosceles trapezoids. Since they're isosceles trapezoids, the bases will be parallel to each other, and the legs will be congruent, which means that this leg will be congruent to this leg, and this leg will be congruent to this leg. But be careful, I want to make sure I use 2 tick marks here so that it looks like this is not congruent to this. If I just use 1 tick mark, these 2 sides would look like they're congruent. Since these two isosceles trapezoids are similar, the corresponding angles will be congruent. And since this is an isosceles trapezoid, the base angles will be congruent to each other, which means that this angle will be congruent to this angle. And since the isosceles trapezoids are similar, these 2 angles will be congruent. So if this angle is 70 degrees, this angle has to be 70, which means that these 2 are both 70. And our lines are parallel, which means that our consecutive interior angles between 2 parallel lines will be supplementary. So both of these angles will be 110. So y is 110 degrees big. Let's look at solving for x. X is a side of the trapezoid, and sides between similar shapes will be proportional. So to solve for x, I need to set up a proportion. I can set up this proportion a couple different ways, but I want to set it up consistently. X is going to be proportional to side 4. Now I could use 6 and z plus 2, but then I'm going to introduce another variable. So I don't want to use these 2 sides. I want to use 10 and 8. Notice I went from here to here, here to here. X over 4, 10 over 8. This proportion will be similar, or consistent. So cross multiply. 8x equals 40. Solve for x. Now I need to solve for z. To solve for z, z is a side, so I'm going to set up a proportion. Now I could use 5 in the second proportion, but I don't have to. I'm going to go with the information that I'm given. I'm going to say 10 goes to 8 as 6 goes to z plus 2. I've set up a consistent proportion. Now I need to cross multiply. 10 times z plus 2. And I need to put z plus 2 in parentheses. This big fraction bar like this says group z plus 2 together. Equals 8 times 6. Now I need to solve for z. Step 1, distribute. 10z plus 20 divide by 10. And if I went to a decimal, my answer would be 2.8. But I want to write my answer as a fraction. Both 28 and 10 are both even, so they're both divisible by 2. 28 divided by 2 is 14, and 10 divided by 2 is 5. Notice my answer for z is written as a fraction. Try to keep all your answers in fraction form unless told to do otherwise. The last thing we need to talk about for similar shapes is scale factor. To find the scale factor between the two shapes, I need to find out what number 5 is being multiplied by to get 7.5, and what number 8 is being multiplied to get 12 for an answer. So I need to think of it this way. 5 times something is going to give me 7.5 for an answer. Since I don't know that something, I need to put a variable there. I can pick whatever variable I want. I'm just going to pick x. And I need to start with 8, and I'm going to multiply by something, and I want to get 12 for an answer. I don't know what that something is, so I'm just going to call it x. Now I have two equations where I can solve for x in both of these equations. To solve for x here, I need to divide by 5. And I started with a decimal, so a decimal is all right for this answer. Divide by 8, divide by 8. 12 divided by 8 is 1.5. So the scale factor going from this rectangle to this rectangle is 1.5. I checked both the height and the width, and I got the same scale factor. Let's look at these two parallelograms. I'm going to start with 8, and for an answer I need to get 12. So I'm going to multiply by something. And I'm going to start with 6, I'm going to multiply by something, and I'm going to get 10 for an answer. 8 times something equals 12, and 6 times something equals 10. I don't know what those two somethings are, so I'm going to put x in there. Divide by 8, divide by 8. To go from 8 to 12, the scale factor is 1.5. 12 is 1.5 bigger than 8. Divide by 6. 10 divided by 6 is 1.6, repeating. So what does that mean for these two shapes? Well, my scale factor from 8 to 12 is 1.5, and my scale factor from 6 to 10 is 1.6. That means that these two parallelograms are not similar. Since the scale factor is the same between these two parallelograms, these two rectangles, are similar.